Hey guys, welcome back. We're going to continue on doing double integrals with polar coordinates. So our problem today is going to take the integration of the region of D of e to the negative x squared minus y squared dA, where D is the region bounded by the semicircle x equals the square root of 4 minus y squared and the y-axis. So I went ahead and got a formula of x squared plus y squared equals 4 by squaring both sides. So we know that this is actually a circle, and it's also going to be on the y-axis. So we're really just looking at this region right here. So there's a couple ways you can set this problem up. I'm going to probably do what I think is the easiest and most direct way to do it. But the first thing we're going to do here is we're going to look at this in terms of polar coordinates. So x squared plus y squared equals 4. So that just simply means that the radius squared is going to be equal to 4. So we have the radius is going to be equal to 2. So the bounds that we're going to use for the radius is going to be at the very end here at 2. And then right here at the origin, we get 0. So that is our region for the radius. Then we're going to look at theta. So you can look at the fact that this is 0, and this is pi over 2, and this is actually negative pi over 2. So the more common thing to do here is actually just say that our region for theta is actually going to be from negative pi over 2 to pi over 2. But what I'm going to do over in my problem set is I'm actually going to change theta. And I'm going to do 0 to pi over 2, and I'm going to double it, right? So really what I'm doing here is I'm finding this, and I'm going to go ahead and double. I just like to keep the less negatives as possible. So I'm going to go from 0 to pi over 2 instead of negative pi over 2 to pi over 2. But whatever you guys want to do is really good. If you did negative pi over 2 to pi over 2, clearly this would not, the 2 would not be there. And then we're going to go ahead and do a 0 to 2 as our bounds for our radius. So just like before, we have seen this many times that if I have e, I have negative x squared. So if I pull out the negative, I am left with, again, x squared plus y squared, but the negative of that. So this is going to be negative r squared, and then we're going to have our r dr d theta. So this is our setup that we're going to be using for this problem. So when we do the problem, we're going to go ahead and leave our theta alone for a second. And this is going to incorporate u substitution, right? So when integrating e to a function, we always make u, well, typically we make our u our function. So the derivative of that function will be negative 2r dr, which again is why that r is there. So that's kind of important that we have it. And we're going to go ahead and pull out our negative 1/2. So I'm going to have a negative 1/2 and then the integration of. So remembering that when you do this, we need to change our bounds. So when we have r equaling 0 right here, this again is what I call the bridge step. This bridges our u to our r. So when r equals 0, then u is also going to be 0. And then when r is equal to 2, our u is going to be negative 4. And so we're going to go ahead and now make this e to the u. Our r dr is our du, and then we have our d theta. So a couple things I want to do because I always love to simplify when I start integrating here, is the first thing is the 2 and the 2 is going to cancel out. And then I'm going to change this, even though it's not required that we do it, right? We can integrate where the upper bound is a smaller number, but I would just like to go ahead and, while I'm doing the problem, flip it back and do negative 4 to 0. And when I do that, that negative goes away, right? Because that happens when you multiply the integral by negative 1, you can actually change your bounds. So e to the u du d theta. So just like to pretty things up before we start integrating a little bit more. So we're going to go ahead and do the integration from 0 to pi over 2. And then we're going to integrate e to the u. Well, that's awesome because the integration of e to the u is just e to the u. And we're going to evaluate this from 0 to negative 4. And again, you could have had a negative out here and flip-flop that. It does not matter. And then our d theta. So if we do a quick little plug-in and chugging in here, we get the integration from 0 to pi over 2. We get e to the 0 minus e to the negative 4 d theta. So let's simplify this down a little bit more. See what color I want to use here. I get 0 to pi over 2 of 1 minus, and I'm going to go ahead and just do 1 over e to the fourth d theta. All right, so we're kind of getting the home stretch here with the problem itself. Once we get to this, it just becomes a very simple ABBC calculus problem where we integrate now with respect to theta. So the integration of 1 is just theta. And then this is also a constant, so I get 1 over e to the fourth theta as well. And then I'm going to evaluate this from 0 to pi over 2. So when we do this, we're going to get pi over 2 minus 1 over e to the fourth times pi over 2. And we're just going to leave this answer alone as is. We don't have to, we can pull out a pi over 2 if we wanted to, and then pi over 2 times 1 minus 1 over e to the 4, but we're okay with that right there. So I hope that makes sense to you guys. I really do like these polar integrations. I think they're actually super fun to do. So the good thing is whatever the parameters were given, draw a picture and just kind of figure out, well, what's my radius and what's my theta. You'll be using this a lot more when we start talking about triple integrals, what's going on with those, and we'll get to those in a later video. So have a good one, and I will see you guys in the next one. Take care.